Hello everybody, welcome back to my YouTube channel. In this video, we will discuss what sequence to sequence models are, and within this class, we will discuss one very important model, and that is encoder decoder model. So till now, we discussed what LSTMs are, what GRUs are. If you haven't watched these videos, I will highly recommend to go and give it a try because I have explained everything in so much detail and in a very simplified manner. So these videos will really help you. I haven't covered yet artificial neural network, convolution neural network, recurrent neural network. These videos will be coming out soon. But from this video, we are starting a new series of model that are called sequence to sequence models. These are special models where the input is a sequence and the output that we are getting is also a sequence. Any example that you can think of where we can mainly a natural language problem where you can use these models? Any example that you can think of? So one example is machine translation or natural language translation. Let's say your input is in Hindi and these models do certain processing, and in output the response that you are getting is in English. So let's say your input sentence was ये है एक टेब है. So in return, what you are getting once the processing is done, you are getting the translated version of this sentence, and that is, this is an apple. This is an apple. So the input is a sequence, a series of words, and the output that you are getting, that is also a sequence or a series of word in another language. So machine translation is one of the examples where sequence to sequence models are used, where you can translate from one language to another language. So that is why sequence to sequence models are very important, because they solve a very important problem, and that is how humans communicate. Many things around it. For example, text summarization. You may provide a very large Word document and you pass it inside your sequence to sequence model. The output is also a sequence, but it is more summarized form of that document that you passed as input. So many other problems like speech to text systems where you are providing an audio input and in return you are getting a text output. So these are sequence to sequence models, and in this class today we will be covering one of its type, and that is encoder and decoder models. Let's start what encoder and decoder models are. So at high level, let's say this is your encoder and this is your decoder. At high level, what happens that inside encoder, whatever sentence or whatever sequence of words you put in, that sequence of words is processed and it is compressed and represented in form of a vector. This vector is nothing but your context vector, just like you had in LSTMs, HT, CT, and in GRUs HT, right? So these vectors, they form the context vector. Now, we will see a detailed architecture, no worries. I'm just giving you a high level overview of what happens. So whenever you pass a sentence as input, behind the scene, encoder encodes it in form of a vector, and this vector is summarized representation of whatever you have passed as input. So let's say I pass that Hindi sentence here, ये है एक सेब है. So what will happen inside encoder, that it will process this sentence word by word, and once the entire processing is done, the output of this encoder will be a vector. What this vector is called context vector, and this represents the compressed representation of input sequence. Whatever sequence you have passed, this vector will be the representation of this sentence in a compressed form. It's not like it's exactly representing this sentence, but in a compressed, summarized form, this vector represents this sequence of words. Now, once you have got this vector, pass this sequence of numbers, which we are calling context vector, inside our decoder. And this decoder decodes this vector and spits out output. And the output is this is an apple. So there is an encoder that takes in your input sentence, processes it, and gives out a context vector, which is nothing but a numerical representation, which which is a more compressed or intact form of the input sequence that you have provided. And that sequence of numbers or the vector goes inside your decoder then your decoder decodes that vector and provides you the output in the output sequence or the output language that you want, if we are considering the example of machine translation. So this is what happens. You have an encoder that understands the text, summarizes it. You have a context vector that is obtained summary of the text in form of vector, which is passed in the decoder. And then you have a decoder that summary is decoded into tokens or words and final output is obtained. So this was the high level overview of encoder decoder model. Now, one question that might come to your mind, and that is, what is inside this encoder and what is inside this decoder? So these encoders and decoders are nothing but LSTM cells. They are built up of LSTMs. If you are not aware of what LSTMs are, I will highly recommend you to please go and watch the LSTM video on my channel. I promise that everything in that video has been very clearly explained in a very detailed and simplified manner. So that video will really help you understand the entire architecture of LSTM cell and what exactly happens inside it. We will not be covering the details here because we have already explained everything in the LSTM video. So inside this decoder, we have a LSTM cell that unfolds in time. You have a single LSTM cell here. Instead of a single LSTM cell, you may have deep LSTMs. Now you might be wondering what deep LSTMs are. Similarly, you have deep RNNs. So these are nothing but instead of a single cell, let's say you have another cell, right? Instead of a single cell, let's say you have another cell that is stacked over it. So let's say this is your first LSTM cell, and over it you stack another one. Okay, so this will become a deep RNN. Now output, instead of coming from this cell, it will come from this cell, and like how it unfolds in time, this cell will also unfold in time. Okay, so if you want a detailed video on this, do let me know in the comment section. I will explain both deep RNNs and bidirectional RNNs in this video, in that video. But for now, let's just come back here. So you have a single LSTM cell here, and in this LSTM cell will unfold in time. So let's say you have this sentence that you're passing as input, then first word will go here, but it will not go as it is. Of course, you will convert them into a vector or a numerical representation that your model can understand. So you will pass that word in in form of a vector, and you have here your hidden state and you have your memory cell state. We discussed everything, right? This is for retaining your short-term memory and this is for retaining your long-term context. So inside this LSTM, the processing will happen and it will unfold in time. Again, you will pass the next word here, add timestamp time step t equals to 2. And once every word has been passed and unfolding in time is done, at the end, what you will get two vectors. First one is ht and second one is ct. Now these vectors that we have got here, this becomes your context vector. So this was your encoder, a single LSTM cell that is unfolding in time, and in output it is giving you HT and CT, which are nothing but your context vectors. Now these context vectors are passed as it is inside your coder. This is your decoder. So now what we have done, that entire sentence that we have compressed it in form of a vector or two vectors here, one for retaining the long-term context and one for retaining the short-term context. So now we have everything. We have the compressed representation of our sentence in form of these two vectors. Now we will take these two vectors and we will pass them as it is inside our decoder. Now this is our decoder. This decoder is again a LSTM cell. Okay, now this LSTM cell is actually different from the LSTM cell that we have here. It can have different weights, right? But the LSTM cell is single, which is again unfolding in time. Now, what is happening here? That you pass here HT and CT, and these HT or CT are nothing but context vector that are coming from the encoders part. Okay, so now inside this LSTM, this is also LSTM, the processing is happening. But now here what we are doing, that what we want is, we want that for this sentence ये है एक सेब है, we want the output as this is an apple. Now this is an apple. In order to get this, what we add here is two additional tokens. The first one is start and second one is end. This start tells the decoder that you need to start translation now. And this end tells the decoder that stop processing. We have got our sentence. We have got we have got our output. So these tokens are necessary, and you get it. You get start from the first LSTM cell and you get end from the last LSTM cell as output. And in between, whatever you get, that is your actual output, that is your actual sentence. Now, here you will pass start. Okay, I think I said something wrong here. This start will be input and this end will be output of last LSTM cell. So this is input of first LSTM cell and end is the output of last LSTM cell. Start is input, end is output. So we pass start from here. Now inside this LSTM, the processing happens and you get here HT. Okay, you get here HT. But you must be wondering that we are just getting HT. How are we getting the words? We will understand that part, but let me just first complete the architecture. Again, these states will be updated and it will go in the next step. This is again an LSTM and this will keep on going until we get the output as end. Now we will see what's happening here. So what exactly is happening here, that when you pass start from here, then it takes in HT, it takes in CT, it does some processing inside it, and in output, it gives you HT. Now, once you get this HT, inside this decoder, you have an additional softmax layer. You have an additional softmax layer. Now, for those who don't know what softmax layer is, so it is nothing but a neural network where the activation function is softmax, where the activation function is softmax. Okay. Now, this neural network, since it's a network, it will have more than one nodes. And this is your softmax layer where every node has an activation function that is softmax. Now, what's the benefit of using softmax? Softmax is amazing when you want to do multi-class classification. When you have a binary classification, then you know either the output is yes or the output is no. But during multi-class classification, you have multiple class that can come as an output. For example, let's say I'm doing a classification where I am classifying whether it's a bird, whether it's a dog, or whether it's a cat. So we have three classes here. So for such problems where we have multi-class classification, use softmax layer as activation function in the final layer, right? So from here, what we will get? We will get a vector, and this vector is nothing but it represents probability. What's the probability of a particular word that this word will come, right? And we pick that probability, we pick that word that is of highest probability, that will be our output. Now it's okay if you don't understand how we are deciding these nodes and why uh, this sequence tells you because ultimately these are just probabilities, then how you are mapping it with the word and how this sequence is fixed on the basis of words that we have, everything will be discussed. But let me just cover this part first. For now, you just remember that this output, this ht that we get, we pass it inside our softmax layer, which is nothing but a neural network where the nodes have activation function of softmax, and the output that we are getting from here is a vector, that is a vector of probabilities. From this vector we are picking up the one that has the highest value, because each value that we see in softmax is a probability and sum of all is equal to 1. So we pick the one that has the highest probability, and corresponding to this probability we check the word and we pick that word, and that will be our final output. Okay, and since our ht is also a vector, so it will be fully connected. Okay, it will be fully connected, fully connected neural network. Now, once you have got the output from here, let's say you got the output, let's say you got the wrong output, because since we have just started our training, let's say we got the wrong output. Let's say instead of this is an apple, we got apple from here. Okay, so clearly this is a wrong prediction. This should be the right answer instead of apple. But since we got apple, what we will do at the next step, that we will always pass the correct input. So actually, since we got apple, we should have passed apple here. But to reduce the training time and to converge faster towards the solution, what we do, that irrespective of the output that we have got during training, we always pass the right input. So we pass this from here. Whatever we got as output in the previous LSTM cell at the previous time step, we pass the correct input at the next time step and at every time step during the training phase. But when you are testing it, once the training is done and when you are actually testing your model, then you pass this output as it is without any modification. Okay, now this process continues, you get an output from here, and then in the next LSTM cell you pass the right output. And this is how from here, whatever words you have got, for example this is an apple, you collect all those words and that is your final output, that is your final sentence, and at the end you will get n from the last LSTM cell as output. Okay, so I think this is clear. Now let's just move to the softmax part and how is it solving our problem. So what we actually do, that let's say you have this start, this is an apple, and you end it. So this is your sentence. Now if I do one hot encoding of it, how start will be represented? 1, and how many words are there? 1 2 3 4 5 6. 1 2 3 4 5. How this will be represented? How is will be represented? So I think you have understood how we are one hot encoding it. right? So these will be the vectors, right? Now, how we define that in our vocabulary, set it. So this will be my vocabulary. 3, 4. I am doing its indexing. Okay, I am doing its indexing. That at first position, this is the word. At second position, this is the word. Now during training, let's say this was my, and I'm talking about decoder because that is where we are using the softmax layer. So during training, what happens that when you pass your inputs here, HT, CT, and your first word from here, that is start, the processing happens here, and then you get an output from here, HT, which is a vector, right? And this vector is passed in softmax layer. Now, during training, what happens that let's say the output from your softmax layer was actually apple, right? But the correct output that should come from here was this, right? So what happened here? What happened here? Your model did a mistake. Now, if I consider the output vector of softmax layer, then let's say that is a vector. For example, 0 0.1, 0 0.2, 0 0.3, 0 0.4. Actually, let me keep it 0 0.2. Okay, and there are 6, right? So 0 0.1, 0 0.1. 3, 3, 6, 10. So the sum is 1. Probability is 1 here. Well, the sum of all probabilities is 1 here. Now, if you see here, let me make this 0 0.3 and this 2 because we want this of highest probability, right? Now, this is what we were expecting for this to come up, right? For this to come up. But what we got actually not exactly this. It should actually be this. 0 0 0 0. So this was the output that we were expecting, right? This was the output that we were expecting. But what we got, I think we should uh Apple should be of highest probability, right? So let me write it nicely. Let me remove this part. Apple should be of highest probability since. So let me make this 0 0.4, 4, 5, 6. That means 2, 1, 1. Now, Apple should is of highest probability. So Apple got selected. But what we were expecting? We were expecting this part or something with where this has the highest probability, right? So what will happen? Our loss function will come into picture, and if there is a lot of difference, it will penalize based on the gradients that we have, and the training will happen. Now, because of this training, what will happen? That this model will know that when Apple came, it was a big mistake from its end. But it would have been better if it got this, right? So during training, it learns that word is actually fixed here and it depends on the vocabulary that you have. I hope this part is clear. I'm again repeating myself. It is because of the training that your model learns that each probability represents a fixed word. It is only because of the training that happens. Because if it is doing a wrong prediction, then during back propagation and the loss that we are calculating, that loss will tell how much error you are doing. But if it's giving a high probability to exactly the word that we are expecting, then it is giving us a very less loss. And if it's one, which is a rare case, especially if you are in the early stages of training, then that loss will be very, very less or maybe a zero if you have if your training has really done really well, right? Training part has really done really if your training part has done something really well. Now it is during training that your system learns, okay, for this word we have this position. So that happens during the training part, that the model learns that. So I hope this part is clear and I hope the training part is also clear. So what will happen that at first time step, start will go from here, then you will get an output. It can be any word, but during training, in the second time step, we will always pass the right word. So this, then in the next LSTM cell, we will pass is, then an, and from here we will pass apple, here we will get and in between we can get anything. But let's say you are testing it, you had your training is done and you are testing it, then whatever you will get an out, you will get as output from here, let's say this, that exact output will go as input for the next LSTM cell. Okay, and whatever outputs you are getting from here, this is an apple, that becomes your final output. You collect all of them and that becomes your final sentence, final output. Okay. And what is the loss function that we are using in this case, the softmax part? That loss function is called categorical cross entropy. I will make a video on this as well, that what are the different loss functions and how, when do we use which loss function. So everything will be covered on this channel. Don't forget to subscribe because that really gives me motivation. Now coming back to our topic, encoder decoder. I hope the architecture part is clear. Now, how the training happens? The training happens with the help of backpropagation. That is the technique that we use along with gradient descent in order to train our weights and biases. Now, what is the improvement that I can do here? Of course, we can have an embedding layer in the encoder part and in the decoder part, that instead of passing this, because actually we are passing the embeddings here, but representing it as a separate layer in the architecture really helps to understand it. Now, instead of one hot encoding, because here we are using one hot encoding, which is actually not a right way of representing words because it does not carry the semantic meaning. A better way would be if we pass a dense vector here, for example, an embedding that we got from word to vec, then that would be great because that is actually the dense representation of your word. Another benefit would have been if we use the deep LSTMs. It's okay if that is not, if you don't understand what deep LSTMs are, we will be covering that very soon. And the third benefit is if you just the out, reverse the inputs. Now you must be wondering that what will happen if I reverse the inputs of encoder only. For example, यह एक सेब है. Instead of passing it this way, what if I pass it like this? यह सेब एक यह है सेब एक यह. Now, what's the benefit of passing it this way? So what will happen in your decoder part, the distance between this and this part will be the least. So it will be able to retain this part in a better way. This is actually good in cases where your initial part of the sentence, your initial words carry more context. But this is not a very famous technique that is used, and generally your sentence is as it is passed. And I also believe that this is a better way of doing it. Now, it's okay. We covered what its architecture is. We covered how we can improve it. But now let's just discuss that what is the problem with encoder decoder model. The problem is that here the sentence was small. This is an apple. यह एक सेब है. The sentence was very small. But consider an example where you have a very long sentence of more than 25 words. What will happen in this case? Know that LSTMs are able to read in context in CT and HT, but and we are not at all questioning LSTM's capabilities there. But the point that I'm trying to make here is that if we have a very long sentence, then we are carrying the information in two vectors, HT and CT. Now, these vectors are nothing but numerical representation of your entire sentence. Now, do you really think that this small vector can carry everything that you have inside your sentence? It is a compressed form, right? If it is more like a summary where you have short term context, long term context, but a summarized view of it. You can't retain every information of your sentence inside these vectors. So that is why we call that there is an information overload that happens here. Because of which, since every information is not captured here, the decoder part is also not able to decode it properly. Okay, because if you were able to pass the entire information, then only decoder would have entirely decoded it. But since that information is not complete here, the output that you're getting from your decoder, that might not be that much accurate. So that is the problem. Now, what is the solution to this problem? The solution is that instead of focusing on the entire sentence that you have, instead of focusing on instead of focusing of input at every time step, or rather I should say that instead of HT and CT, this is the final, right? This is the final output that we get from the encoder. Now, instead of focusing on everything that you have got as output, it would have been better if I can only focus on those part of the sentences from where that translation really works. So let me put it this way. Uh, let's say you have a sentence here, यह एक सेब है, and your output is this is an apple. This is an apple. Now, in these two sentences, we know that translation of save, for translation of apple, we need to only focus on save, right? In order to get the translation, in order to get the output of translation as apple, the only word that you need to focus on is save. You don't need to know the entire sentence, entire input sentence for it, right? You need not to know everything about what your CTHT is, final outputs. The only word that is actually important in translating or giving output apple is save. So it would have been better, instead of passing the entire sentence, or instead of passing the entire context of the sentence as input, it would have been better if you could pass the information that this word at this time step, this hidden state at time step t equals to 3 is most important in obtaining apple as output. This is where we will study attention mechanism. So the solution is to provide input at each time step of decoder, that which time steps hidden state from encoder is important for translation currently. This is what attention mechanism is. And we humans also translate it this way, right? Let's say we are translating a very big story. Then what we will do, that we will only focus on the part that we are currently reading, right? For example, there's a sentence, a very big sentence, that my name is Nick and I have a YouTube channel. I do a lot of hard work there. Then, if I'm translating this sentence, then I will only focus on the part that I'm currently translating and everything around it, not the entire full story that I have heard, right? Only a certain part I focus. So that is how we humans also translate. When we are translating a particular part, then we are only focusing on that and context around it, but not the entire full story. So in the next video, we will cover attention mechanism in detail. And I hope you like this video. Please give it a thumbs up. If you have any doubts, do let me know in the comment section. I will try to solve all of them. And if you haven't subscribed, please subscribe to my channel, because I have been doing a lot of hard work. So thank you.